Let's look at the integral test. The integral test says this: let f of x be a function, be a continuous function that decreases to 0 as x goes to infinity. And also, let a sub n equal f of n. Then, the series a sub n, n from 1 to infinity, is convergent if and only if the limit, not the limit, the integral from 1 to infinity of f of x dx is convergent. So, two things I should probably mention. This test says that this series and this integral do the same thing. Either both converge or both diverge. If they both converge, they are not equal. So just keep in mind, this tells you that they both converge or they both diverge. But if they both converge, then if you were to actually somehow find this sum and also evaluate this integral, they're not going to be the same value. They're probably going to be fairly close, but they're not going to be exactly the same. All right, let's look at an example. This right here, 1 over 4n plus 1, and n goes from 1 to infinity. All right, this function, if we extract this function, this would be like f of x is 1 over 4x plus 1. And if you think about it, that is a continuous function, and as x grows large, f of x decreases to 0. So what we want to do is integrate this function from, let's see, we can't do from 0. It's supposed to be from 1 to infinity. And before we do that, let me just mention one thing back over here. When I see this, the first thing I would do would be use the test for divergence on it. But notice as n goes to infinity, this goes to 0. The terms go to 0. So therefore, the test for divergence tells us nothing. All right, so we've got to do this integral. This integral, we've got to use u substitution. I'm going to let u equal 4x plus 1. du is going to be 4 dx. And my endpoints, I'm not going to write them down. I'm just going to calculate them as I put them over here. The bottom endpoint is 1, so my new bottom endpoint is going to be 5. My upper endpoint is infinity, so my new upper endpoint is 4 times infinity plus 1, which is still infinity. This becomes 1 over u, and then dx gets replaced with 1/4 du. All right, so I'll pull that 1/4 out front. 5 to infinity of 1 over u du. So I get 1/4 natural log of u from 5 to infinity. When you plug those endpoints in, we get this. Now keep in mind, this is shorthand abusive notation. What this really means is what happens to natural log as x goes to infinity. And the answer is this goes to infinity minus 1/4 ln 5. So infinity minus some finite number is infinity. Therefore, this thing diverges. This is not the only way that we could show that this diverges. Another thing we could do is use a comparison test with the harmonic series, but that's in the next section. Let's do another example. Let's look at this. 1/2 plus 1/5 plus 1/10 plus 1/19 plus 1/27. I'm sorry, that 19th should actually be 1/17. And the 27 should be 1/26. Now, it's not at all obvious what this is, so I'm going to give you a hint. This is based off of 1/n squared. If you look at these, it's 1/n squared plus 1. And n goes from 1 to infinity. Again, the test for divergence would fail on this because as we go to infinity, the term here, 1/n squared plus 1, is going to go to 0. But we can use the integral test here. So let's do that. I'm going to integrate 1/x squared plus 1 dx from 1 to infinity. Now, what does this integral give us? Integrating 1/x squared plus 1 gives us inverse tan of x from 1 to infinity. So if we use the abusive notation, we get inverse tan of infinity minus inverse tan of 1. Of course, what this means is this is a limit. It's saying, what does inverse tan do as x goes to infinity? Well, if you graph it on Desmos or your calculator or by hand, if we graph y equals inverse tan of x, it looks like this, and this asymptote over here is pi over 2. So this gives us pi over 2 minus inverse tan of 1 is pi over 4. So we get pi over 4. And so that's a finite number, and so the answer is that this converges. Let's do one more example. Suppose we have this integral of natural log of n over n. N goes from 1 to infinity. All right, so this sum. First thing to do, of course, is do the test for divergence. If we look at this, I'm going to write it out. Check the test for divergence first. If you take the limit as n ln n over n goes to infinity, n grows faster than natural log of n, so this gives me 0. So the test for divergence tells us nothing. So let's use the integral test. I should technically change this to an x. If you leave your variable as an n, it doesn't really matter. But let's change it to x. Typically, n is used as an index where the variable only takes on integer values, and x is used for normal variables. So anyway, to do this, we want to use a u substitution. Let u equal ln x. du is going to be 1 over x dx. So the integral becomes, let's see, just u du. And my endpoints, on the bottom, I get ln of 1, which is 0. And on the top, I get ln of infinity, which is infinity. All right, when I integrate this, I get 1/2 u squared. So I get 1/2 of infinity squared minus 1/2 of 0 squared. So it's an infinite number minus 0, so it's infinity. And therefore, this thing diverges.